Thanks. I'll begin with a word of prayer. Just a second here. That's better. There's a lot of noise in that hallway. Heavenly Father, we thank you for this day. I thank you for these students who be with us today. Help us to just be able to apply what we learned last class to some interesting computations. Just guide our work, Lord, today. In your name I pray. Amen. So I showed you the implicit and inverse function theorems last time, right? And we looked at, I give you some sort of intuitive sketch why they're true, right? And so today I wanted to show you how those theorems, especially the implicit function theorem, goes to solve problems of calculus, all right? So basically I'm going to look at implicit differentiation in a somewhat general context. Sometimes this topic is referred to as differentiation with side constraints, so implicit differentiation. And so the problem we want to consider is the problem which you actually face in problems of application so many times. You have some system of equations, let's say x1 through xm, y1 through yn. So some function g1, some constraint, all right, that's equal to k1. And likewise for g2. And so forth. You got a bunch of these equations, right? I'm going to say I've got n of them. And so, if you don't mind, I could well, fine. I wrote that much, I'll write it again. So the same dependence on, well, not the same dependence, but the same list of independent variables here. So suppose these are given constraints, all right? Then essentially the problem is, you know, as you're analyzing this system, which is described by these equations, what can you choose as dependent variables? What can you choose as independent variables? And how do you calculate partial derivatives with respect to these different variables? That's the thing we'd like to understand. So, how to calculate partial derivatives subject to these constraints. So let me just kind of walk you through the general derivation here for a second. So the way to think about this in terms of just straight computation is what I do is I just take the differential, the total differential of each equation. All right, so when you think about the total differential, you can think of it in a formal sense as just, you know, let me just write down the total differential of g1 and you'll see what I'm talking about. So dg1 is what? It's partial g1, partial x1 dx1, plus partial g2, partial x2 dx2, plus partial, I said g2, I meant g1, sorry about that. These are all g1s, okay? Partial g1, partial xm, dxm. Yeah. And then plus partial y1, dy1, plus plus partial, that was a g1, partial g1, partial yn, dyn. All of that is equal to the differential of k, right? What I've written modulo the differential of k1 on the right hand side, that actually is the definition of total differential, all right? Just formally speaking. But it will also match, in fact, the Frechet derivative of the function g1 with the appropriate interpretation. What is the differential of a constant, though? That's 0, right? And likewise, I won't do d2, I'll just write down for dgn, same song and dance, but replace n with, you know, 1 with n, So we have these equations involving differentials. I mean, I would call it a differential equation, but that means something else. But as you can see, these equations are what? These are linear in the variables what? Let's say dx1, dxm, dy1, dyn, right? So computationally, right, this is a way to essentially linearize the nonlinear equation. You just take the differential of it. Each equation, it leaves you with a linear equation in the differentials in this way. So then you can rewrite this, right? You can rewrite this in terms of a column multiplication, something like the following. You can rewrite this in matrix notation, something like this. You can say, well, what that really is partial x1 of g, partial xm of g. This matrix times the column vector of differentials dx1, dx2, dx, dxm, and then plus this matrix of y derivatives, partial y1 g, concatenated all the way down to partial yn g, times this column vector of dy1, dy2, column vector of differentials dyn, equals to 0. Again, just formally realizing the differentials you can think of as variables. So we can do linear algebra on the problem, which is matrix. And then, of course, I can solve for the column vector of y differentials. How? Let me just suggest yet another notation. So what I've got here is partial xg times the dx vector plus partial yg times the dy vector. How can I solve for the dy vector? Dy vector is equal to what? Mm-hmm. Right, inverse of this guy, right? Whatever that's called, times partial x. Call it 7? I will not call it 7. We've talked about this. How dare you, sir?
Come on. 0. All right.
Yes, there are no numbers. I have not. Wait a second. That is not true. I have 1. I have 2. I have an m.
Again, those are variables.
1 is not a variable. Only in your strange world of numerical variables is 1 a variable. Although I would add that using 1 as a variable would do more damage than using 7 as a variable.
True. That's why I suggested 7.
Oh, I see. So that's why 7 is a fair suggestion. Oh, yeah, okay.
And that's why, like, I didn't use 2. I mean, hidden in the dots, there is a 7. Like, eventually, the dots, hidden in the dots.
Jess has a point. There is a 7 somewhere in there. Just like there's a 3,400,347. Okay, so what this is actually, and so what this shows you is I can solve for dy I can solve for dy as a particular linear combination of the dx's, right? I can solve for dy as a particular linear combination of dx's, provided which matrix exists, provided partial y g inverse exists, right? Now remember last time we talked about the implicit function theorem. What did the implicit function theorem tell us? It told us that you can write y as a function of x in precisely this situation. In other words, the condition that allowed me to solve for the differential of y in terms of the differential x is precisely the same condition that last time showed us that you could actually write the y variables in terms of the x variables.
So it's just essentially just an extrapolation.
Right. In other words, the implicit function theorem justifies the conclusions I'm about to make formally from this differential calculation.
So we should make
Now, so the way to understand this then is what this is going to give you is, well, let me just, so if I look at, for example, dy, let's say the jth one, that's going to be, you know, I don't know, I don't want to write that again. Let me just say it's going to be partial yj, partial x1 dx1 plus da 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 plus partial yj, partial x. How many x's do I have? M. Dxm. Excuse me, partial xm. So I can read off the partial derivatives of y with respect to the x1 through xm, you know, from star. Because this actually gives me a formula for the differentials, and the meaning of each coefficient is it's the partial derivative. Well, oh yeah, y sub j.
I mean, like, why is it sub j? Where's that?
Oh, I'm saying this is good for, I mean, dy vector is dy1, dy2, da da da, dyn. I get this for j equals 1 to, I mean, this is for, I don't want to write n things. I'm just saying for j equals to 1, 2, da da, n.
Oh, okay.
You have this.
Sorry.
So this is you know, this is the idea and the general idea of how to calculate partial derivatives using differentials. Let me show you some examples that will make more sense probably. So here's an example. Suppose I have the problem f of x, y, z equals to a constant k, right? I calculate the differential of this. And I get what? I get fx dx plus fy dy plus fz dz. Okay? From this, and that's equal to 0, right? If I'm looking at the level surface. So then I can ask questions like, for example, let me just say question number 1. What is partial z, partial x? So what do? The answer is solve for dz. I get dz equals to what? dz is equal to minus fx over fz dx plus, minus fy over fz dy. So from this expression, I can read off partial derivatives of z with respect to x and y. Like from this, I can read off directly that partial z, partial x is equal to minus partial fx, f sub x, f sub z. That should save some writing to use the partial derivative sub-index notation here. What's partial z, partial y? Minus fy over z, right? fc. There's my first question. What's my second question? what is partial x partial y equal to? So let me start to emphasize what's going on here. In my first question, which are the independent variables, which is the dependent variable? Z is the dependent variable, and x and y are independent. In my second question, I'm proposing that x is a dependent variable. By process of elimination here, in context, it has to be a dependent variable on y and z. So the implicit function theorem says I can write x as a function of y and z precisely when the partial derivative of f with respect to x is non-zero, which of course is the same condition I need to solve this differential, equation involving differentials for dx. Sorry, I'm trying hard not to say differential equation. Let's see here, dx is equal to, so minus, let's see here, minus fy over fx dy minus fz over fx dz, and there you have it, partial x, partial, let's see here, partial x, partial what? Partial x, partial y is equal to minus fy over fx, and partial x, partial z is equal to minus fz over fx. Yeah, what would happen? What's the same story for y? Let's see here. So for y, third question, partial y, let's see here. What do I want to calculate? Oh, partial y, partial z. How about that? Among other things. So what you do is dy is minus fx over fy dx minus fz over fy dz, and we find from this that partial y partial x is equal to minus fx over fy, and partial y partial z is equal to minus fz over fy. So then you get one of the interesting equations here. If we calculate partial x partial y times partial y partial z times partial z partial x, what do you get? We get minus 1. It's true. You remember that from Calc 3? Okay, yes. We can work it out though. What's that? Yeah, it's not hard to exactly, but you'd be tempted to think this is 1, right? Because the partial derivatives like cancel out. So like in terms of some kind of formal chain rule, you'd be tempted to think it's 1, right? Because the x's kind of cancel, the y's cancel, the z's cancel. And we've seen many instances where basically dx over dx cancels to give you 1 in one sense or another, right? But here, when you put this in context, what is partial x partial y? Well, partial x partial y is negative fz over fx. And what's partial y partial z? Well, partial y partial z is up here somewhere. Minus fz over fy. Did I do this wrong? Partial x partial y was what? Fy over, oh, that was supposed to be fy.
It's okay, you need plus.
Fy over fx, though. Partial x partial y was minus partial fy, minus fy over fx. Then I have fz over fy, and then finally I have what? Yeah, fx over fz. And as you can see, the y's cancel, the z's cancel, the x's cancel, and as Daniel had forecast, it is in fact minus 1, yes. But I personally find these kinds of expressions very dangerous because they're really kind of hybrid, in the sense that mathematically they're really kind of, if you start thinking about functions and mappings and domains and ranges and all that kind of thing, this is really a rather weird expression because in this single expression, I'm treating y and x and z both as dependent and independent.
Isn't that what partials do?
Well, yeah. I mean, that's part of the reason we talk about partial derivatives is, yeah, they allow us to treat some functions as independent, some as independent, but if you don't have that in mind, it does lead to confusions. I mean, so, I'm going to show you an example of that. Of course, by the way, I mean, I should mention perfunctory example. If you have PV equals to nRT, where n and r are constant, then by the same logic, basically, partial p, partial v, partial v, partial t, partial p is minus 1. Basically, here I've just let f of the function pvt equal to pv minus nRT. And of course, now that I gave you a formula, you could actually work out that it's minus 1 in terms of explicit partial derivatives, right? Like, for example, partial f, well, sorry. Yeah, this is the ideal gas law. Pressure, volume, temperature, number, was that Boyle's constant? I forget. I don't know. So for this one, on the one hand, partial p, partial p, partial p, partial v would be what? It would be, well, I don't want to do that. I'm sorry. Let me do more interesting examples. You could actually explicitly calculate these, but this one you would hold what? You hold t fixed. This one I would hold p fixed. This one I would hold v fixed. So this has independent variables, volume, temperature. This has independent variables, temperature, pressure, and then independent variables, pressure, volume. Let me show you another example. I think this is a good example. If you guys don't mind if I stick with my notes, because I know from experience that if I just make up stuff here, there's no telling what will happen. X plus y plus z plus w equals to 3, and x squared minus 2xyz plus w cubed is equal to 5. And then the question is, calculate partial z partial x. That's actually not the question that's asked, but I want to point out why that's a bad question as it's currently stated. So partial z, partial x, like what does that mean in this context? I've got 4 variables, I've got 2 equations, right? So that means that if these equations are independent, they're independent. Okay, I mean, these are genuinely different equations, right? It's not hard to see that. I mean, maybe there's some sort of pathological set where they're the same, but ignoring, I don't even know about that. I'm not sure about that. Anyway, the question, though, is partial z, partial x. What does that mean? See, because there's 2 different things you could think about. Is this partial z, partial x, holding y fixed, or is this partial z, partial x holding w fixed? Those would be different partial derivatives.
You can't solve both things?
No. I mean, the implicit function theorem says I can solve for 2 variables in terms of the other 2. I mean, what you're saying, if I held them both fixed, that would be a further constraint.
Okay.
Yeah, I think. Or let's see, if I hold both y and w. If I hold y and w fixed, then I don't know what this means. I mean, then then I'd be differentiating with respect to a dependent variable. I would need to think about what that meant. If I hold y and w fixed, I don't know what that means. I'm sorry. I don't know how to interpret what you said. Okay, so to calculate partial z partial x holding y fixed, you can do like that. Let me just show you, there is a way. If I say I'm going to calculate, let me show you the way I would teach, say, Calculus 3 students who don't know about differentials. All right, so if I want to calculate partial z partial x holding y fixed, what that means is that x and y are independent, right? So how do you characterize independent variables? In a nutshell, it's simply this. Partial x, partial y is equal to 0, and partial y, partial x is equal to 0. So that they have no bearing on one another. So with that in mind, I've got options, right? So I basically use the given constraint equations, and I differentiate with respect to x. So, we call this 1 and call this 2. So I take partial x of 1, and you get the following. You get what? You get 1 plus partial y partial x, which is what? 0. Partial differentiate, so I get partial z partial x, which is what I'm after, plus partial w partial x is equal to 0. And then what do I do? I calculate the partial derivative of 2 and see what that tells me. So partial derivative of 2 with respect to x gives me 2x minus, I'm going to write this down, 2 partial x of this expression x, y, z. Well, actually, y is a constant, right? So I can pull it what? I can pull the y out. So let me just go ahead and do that. So minus 2y times partial x of xz plus 3w squared partial w partial x is equal to the partial derivative of 5, right? Which is easy. That's 0. Okay. Now, I got to do the product rule here. So I get 2x minus 2yz minus 2xy partial z partial x plus 3w squared partial w partial x is equal to 0. I now have 2 equations and 2 unknowns. What am I after? I'm after, so I got this equation here, and I got this equation here. I'm trying to solve for what? First time this semester. I don't think it's the first time I've actually got one in this whole semester. Sad. So what would you, I think I like to, I don't know what you guys want to do. We want to solve for partial z partial x, so. Okay, so yeah, partial w partial x is equal to, you say minus partial z partial x minus 1, right? And then plug that into here. And so I get 2x minus 2yz minus 2xy partial z partial x plus 3w squared parentheses minus partial z partial x minus 1. All of that's equal to 0. Now just solve for partial z partial x. Partial z partial x is equal to 2yz minus 2x plus 3w squared, all divided by minus 2xy minus 3w squared. There you go. You guys see it? Now, I mean, this is a way you can calculate, right? But it's not a very good way, because if I ask you other related questions, for example, okay, great. Now, what's partial z partial y? What would you have to do? All over again, right? There's a by far easier way of computing these partial derivatives. It's to take the differential of 1 and 2 and to solve for the appropriate differentials. So let's do that. I'll do it over here. Let's see here. So the differential of 1, what's that give me? Dx plus dy plus dz plus dw equal to 0. Then I get 2x dx, taking the differential of 2 gives me 2x dx minus, oh, now this is kind of complicated, but it's not too bad. So I get 2yz dx minus 2xz dy minus 2xy dz by the triple product rule, basically, plus 3w squared dw equal to 0. I just clean it up a little bit. So I'm interested, I want to solve for what? I'm going to try to, I want to isolate what? If partial z partial x holding y fixed is goal, then z and w are dependent. They're dependent, the dependent variables, which means I want to solve for dz and dw in order to find their partial derivatives. So what I want to do is I want to isolate, I want to solve for dz and dw. So what you're going to do then is you're going to put all of the dz dw terms on one side and all of the dx dy terms on the other. Right? Think of dx and dy as being given things, whereas dz and dw are the variables that you're trying to solve for in this context. So the first equation is easy, right? dy, dz plus dz, not you guys, me. dz plus dw is equal to minus dx minus dy. That one wasn't too bad. Yay. Okay. The second one, I got to collect some terms, maybe. Oh, maybe not. It's just what? Minus 2xy dz. Yeah, plus 3w squared dw is equal to what? Yeah, let's collect together things. This and this. Is there any other dx here? No. So I get 2yz minus 2x. I could have factored the 2 out. Oh well, it's too late. Dx. And then I've got y terms, right? So just plus what? Plus 2xz dy. And then I can look at this as a matrix. See, what this is 1, 1, minus 2xy, 3w squared. It's a symbolic matrix, but a matrix nonetheless. And dz dw is equal to, minus dx minus dy, and this stuff, 2 times yz minus x. I factored the 2 out. Are you proud of me? Plus 2xz dy. This is like that symbolic dy vector is equal to matrix times, well, it's not quite that yet. This is like, in our original notation, what we're looking at, just to kind of bring it back to that, this would be interchangeable with the original equation, something like partial g partial x dx vector is equal to minus partial g partial y dy vector for what it's worth. This stuff is like that stuff from the beginning of the lecture. But so anyway, who cares what the connection is with the original part of the lecture that much? The question is, how do you solve for dz and dw here? What's that? Multiply by the inverse. What did you say, Joe? Yeah, two main choices here. Multiply by the inverse, or what will be nice for 3x3 systems if you faced it, Cramer's rule. Right, you could use Cramer's rule here. It's a good application of Cramer's rule. Or I'll do multiplication by inverse, though. So if this is A, then A inverse is what? So I get 1 over 3w squared plus 2xy times the matrix 3w squared minus 1, 2xy, 1. That's the inverse of that matrix. And then times this column vector of differentials. What do we get? I get that reciprocal function out front, and then I get a 2 vec. I get 3w squared times minus dx minus dy. Minus what? 2 times yz minus x dx minus 2xz dy. And then downstairs I get 2xy minus dx minus dy plus box, no, plus 2yz. If only I had to use 7 for all of this, it would be so much clearer. Let's see here, tx plus 2x z dy. Now what's this tell me? What's partial z partial x equal to then? Right, so we can equate, this is a column, right? So this, whatever it is equal to all of this. Keep in mind the fraction up front, right? And partial z partial x is going to be the coefficient of dz, coefficient of dx, rather, in dz equals stuff, as that stuff. So what is that actually? I don't actually need to, I can read it off from this already. I don't need to write more. I've got minus 3w squared. Let's see here, and then the other thing with dx is this, right, which gives us plus 2x dx. Well, I mean plus 2x rather. The dx is not part of this, okay, plus 2x, that's a dy, right? And then divided by 3w squared plus 2xy. Mm-hmm. Ah, yeah. Oh, hey, what do you know? But if that was it, that wouldn't be too impressive. The thing is, I can also calculate partial z partial y by looking at this the same, right? Partial z partial y is what? Minus 3w squared minus 2xz divided by 3w squared plus 2xy. But the goodness doesn't stop there. I can also calculate partial w partial x and partial w partial w, partial y, also easy to calculate just from reading off coefficients. I'll just do partial w, partial x. Partial w, partial x would be minus 2xy plus 2yz minus x divided by, of course, the same 3w squared plus 2xy. The significance of the denominator, right? That's the determinant of the matrix that we need to be invertible in order to find z and w as functions of x and y. Its significance is told to us in the last class in the implicit function theorem. This is a very general technique. You have a system of equations, you take the differentials, you solve for the ones you're interested in as dependent variables in terms of the rest of them. That will reveal all the partial derivatives that you want. Oh, the denominator? It depends on which way you're asking that question.
Like for dz dx, where does the denominator come from?
It came from, I think it ultimately came from this expression here. It's really the 1 over the determinant of this matrix, which is the criteria you need for this matrix to be invertible. If you go back, yeah.
So it's just reading the coefficients of the top column, and then of course you would have to divide through by the.
Oh, right, yeah. And that was the mechanics of that calculation, yeah. Now, I don't think I haven't completely made my point clear here. I mean, this is good, but this notation, I don't really approve of the notation I have on the board right now. Like, I really insist that we write this. I really think it's better to write this like that, right? To indicate, I like a notation which explicitly indicates the independent variables, because there's ambiguity here. You can also calculate partial z, partial x holding w fixed. And that wouldn't necessarily be the same thing, because there you would be taking the differentials and solving for, you'd solve for dz and dy, and you'd get different coefficients. You wouldn't get the same partial derivative. Let's see if I have that. I don't know if I have it here. Yeah. So if you look at example 4.3.6, there I actually show you an explicit example where partial z, partial x holding y and z fixed gives you 0, but partial z... That's new. I've been kind of spoiled. Like, I've been the whole semester without janitors regularly coming into my classroom. A couple of semesters ago, there's this time I met where without fail, somebody would come in and interrupt our meeting. And it was not like, it was regular too. It was like every single Monday, Wednesday, Friday, they would come in at like 5 o'clock and go, "Oh, you're still here." Like, yeah, we're always here at 5. Every single day of the semester when you come in, we have been here. And he didn't stop. He kept doing this. I think he just wanted us to get out of there faster so he could finish his job, but I don't know. That's my guess. So partial z, partial x holding y and z fixed is 0, but partial z, partial x holding y and w fixed is minus z over x. So if you look at example 4.3.6, I show you an explicit example where the partial derivative of z with respect to x gives you different things depending on what you hold fixed. All right. Let's see here. Let's look at some examples. Let me use the projector here. Wake up. So you guys have a good weekend? It was good. Restful? No? Oh, I actually have solved the first mission. I'll post the solution. I haven't scanned it. I need to print out the actual problem statements so I can put it at the start of the scan. I haven't done that yet, and that's what's kept me from posting it. But where was I? Yeah, I grade it. Everybody else who's taken this class is gone, long gone. Well, at least most. I mean, not too long gone, but gone.
Wait, so
Or
should I
dead.
give it to you now then, since you gave it back to me?
Oh, are you done with it?
I guess. I mean, if you're going to post up the solution.
Hopefully soon. Now, do you want to work on it more? You can just not look at it.
I don't think I have it with me, so I'll just give it to you as soon as I get it.
Okay, that works for me. As you guys know, the homework is for you guys to learn, so. So I was just going through these fun facts with you. We did that example. Oh, what on earth just happened? Okay, I think I just hit the end button. Why is there no undo? I want to undo what I just did. Forgot to tell you to bring your Dramamine. Come on. Oh man, look at all this fun stuff we're gonna do. Come on, where'd you go? 7, 6. By now I should have gone back to the start and clicked on my silly, Come on. All right, here's the example I was just talking about. If we have W equal to XYZ, and that's the equation, then if I calculate, let's see here, star, and so what am I doing? Do I have two equations? I just have one equation. So let's see here. On the one hand, I calculate partial z partial x is minus w over x minus x squared y. Oh, okay.
Wait, it looks like you took all three to be independent in that bottom right.
Yeah, here I have four variables in one equation. C partial. I'm sorry. I'm I don't know. I'm saying I'm holding XYZ and then XYW. Oh, I guess this is the... Oh, duh. So if z and x are independent variables, right, partial z partial x is 0. But if z is the dependent variable, then partial z partial x is minus z over x. So this is, yeah. So it's really different, interpretations here. I mean, yeah. Sorry, let me not get confused. There's nothing to be.
Why would you take the partial with respect to a variable of an independent variable, though?
do it all the time.
We do.
Yeah.
Is it always zero? Or is it not always zero?
It is, but that's the bread and butter, right? Like of calculus 3. I mean, I ask people to do stuff like differentiate this, right? And you're like, oh, okay, so it's 2xy. Game over. You know? So what are you doing there? You're considering partial y, partial x to be 0, right? So yeah, I mean, we do that. The weirder thing is supposing that partial y, partial x could not be 0 because y is a dependent function on x. That's the more complicated thing that we have to think about when we have side conditions. That's the new thing that you probably didn't think as much about in Calc 3. Let's see here. So again, here's just another example. If I have w is equal to x plus y plus z, and if I have x plus y is equal to wz, I can calculate partial w partial x with holding y fixed and partial w partial x holding z fixed, right? But I have to, I have to choose what's dependent and what's independent to make sense of the question. So partial w, I mean, I have done that. I've told you that x and y are going to be independent. This was not, I mean, the question is not unambiguously stated. It's not ambiguously stated. So one way I can do it is just to formally calculate, right? Take partial derivative with respect to x of the equation for w, since I have it. Differentiate, and I get that, right? And then I can basically just do hand-to-hand combat with the equations using the fact that partial x, partial y is equal to 0, and partial y, partial x is equal to 0. Whereas the w and the z are functions of x and y. So I have to respect that basically with the chain rule, and eventually I get to this, right? So I'm sorry, I'm starting to get bored of this. We've already done one of these, and so anyway, I will give you some homework like these, and it's not actually that bad. Oh, here's that example. Oh, by the way, here's the two-dimensional version. Here's the two-dimensional version of the of the product, like the canceling, giving you. This actually does cancel to give you 1. Yeah, because you get -1, -1. In fact, you can start to see if you have, f equals f of n variables equal to a constant. This sort of, product of. Yeah, 1, -1, 1 for the even dimensions, -1 for the odd dimensions, and yeah. Now, the constant rank theorem is something I claim, but I don't have formally stated in the notes. Basically, the idea is this: whatever the rank of the Jacobian is, all right, for a mapping from say Rm to Rn, the rank of the Jacobian at that point gives you essentially the dimension of the image near the point. So, like if my Jacobian has 2 linearly independent columns in it, and if I look at what the mapping is doing close to that point where those two columns are linearly independent, the image is going to be some sort of like surface. It's going to be a 2-dimensional thing. Yeah.
Rank is just number of column vectors.
Rank is the number of linearly independent column vectors in the matrix, or you could say it's the number of linearly independent row vectors. Yeah, it's the same. Both are the rank. Yeah, the number, it's all about the pivot positions. You same number of leading ones, the same number of pivot columns as non-zero rows.
The number of vectors in a spanning set would be equivalent.
Well, linear independence is key though. So spanning.
Number of vectors in a spanning
Well, and a
set.
basis, I guess. And a basis would be.
Yes, if you find a basis for the column space of the Jacobian, that will be the number of things in there is what I'm talking about. If the Jacobian has rank 1, if it just has 1 linearly independent column, then the image is like a curve. If it has no linearly independent columns, that means that it's the 0 matrix, and it means that it's constant. It's a point, 0-dimensional. If it has 5 linearly independent columns, then the image is going to be 5-dimensional, and so forth. This is essentially the constant rank theorem, that the number of linearly independent columns in the Jacobian basically tells you what the image looks like. So as we can look at some examples, like here, f of t is t squared, t cubed. This is the twisted cubic. Its graph is space curve is something like yee, yee, yee. It comes with the sound effects, but so that's a nonstop curve. It's a regular curve everywhere except for one point. Yeah, 0. But so there, I guess I can't conclude anything from the constant rank theorem, but it's non-zero close to there anyway, so not too bad. And so this has 1, but in fact, even that's not even true. Excuse me. At time equal to 0, this still has rank 1. So it's still, still a smooth curve close to there. If you had something like, if it drops down to rank 0, it might still be a curve. It might be a place that you have like a cusp in the curve or something like that. That might be a place where you drop to rank 0. Or you might even have the Jacobian undefined there. I don't know, I'm not sure. I haven't thought about it too much. Here's another example. If you have the dot product mapping, that's a mapping. I take a pair of 3 vectors and I spit out a real number, right? So you can think of it as a mapping from R6 to R, right? And so variables x1, x2, x3, x1, y1, y2, y3. The formula, of course, is this. What's the Jacobian? The Jacobian matrix is a 1 by 6 rather row vector, and there it is. I say it has rank 6. Oh, that's just nonsense. Why has no one complained to me about this over the many years I've taught advanced calculus? This has been wrong for like 4 years. It is rank 1. These are numbers. It is rank 1 provided at least one of these is non-zero. Oh man, embarrassing. But more embarrassing for my students. Have not told me this these many years. Shame on you and your predecessors. See how I turned that around? Okay. Seemed like what? And here I for some reason decided to then do it for n dimensions, and I probably have, at least I'm consistent in my error. Of course it is rank 1, provided at least one of those is non-zero.
So you know what the issue is, Martika?
Yeah.
Need Landon in here.
Yes, if Dr. Professor Landon is here, these mistakes would be rooted out with brutal efficiency. But, efficiency is the wrong word, but they would be rooted out. This much is true. You can't support a larger, like the dimension you're going into, that's the upper bound on the possible rank for the Jacobian. So if I'm mapping into a 10-dimensional space, I can have at most a rank 10 Jacobian. If my mapping is into a 6-dimensional space, the rank of the Jacobian can have at most 6, just by dimensions. Maybe I'll get this right. I don't know. We'll see here. So suppose you have the mapping f of xyz equals to xyz, yz. Here's the mapping from R3 to R3. The Jacobian matrix is this thing. And let's see here. How would you, that's going to have, well, that definitely doesn't have rank 3 if y and z are both 0. Or if one of y is z. If either y is equal to 0, or if z is equal to 0, that means the first column is 0. So it has a rank at most 2. But the second 2 columns, they cannot be linearly dependent. Look at their structure. Like there's no way that one can be a multiple of the other. So the rank of this is at least 2 at all points. Right? And it's going to be rank 3 at any points where y and z are both